kinetics, ठीक है? तो रही you missed the last chapter, लेकिन we'll cover that again, ठीक है?
Okay.
अच्छा, इसमें and you just missed one lecture as well. Yeah, I did send you. I'm just going to recap everything. Okay, what happens in reaction kinetics? The first thing is last time I mentioned that reactions happen because there are collisions, particles colliding with each other. So collisions ka hai ki it depends on the frequency of collisions and the effectiveness of collisions. How many times are the particles colliding with each other, and how strongly or vigorously or effectively are they colliding? So you could have a lot of collisions, but you can have no effective collisions, and the reaction will not happen. And you can have, I mean, the frequency of collision could be very low, and the effectiveness could be very high. So the reaction, speed of reaction depends on both things. There are 5 factors which you've studied in AS, in O levels as well. One is temperature. The higher temperature means more kinetic energy, which means the frequency and the effectiveness of collisions would both increase. Particles travel faster, so there's a higher chance or a higher rate of collisions. And because they're traveling faster, they collide more effectively as well. The concentration, you have more particles per unit volume, so that would mean that you are going to have more frequent collisions, not effective, but frequent collisions. Third one was pressure, and that is for gases only. You have a higher pressure, the particles would be closer to each other. So again, you're just going to have more frequent collisions. Okay? The proportion of effective collisions, it pretty much remains the same. Or the last one was surface area not the last one, the fourth one was surface area. Smaller particle size, you have more frequent collisions. Powdered, you have more frequent collisions. फिर क्या था catalyst? ठीक है, you've got catalyst. So when you have catalyst, what do? They lower the activation energy. And the frequency of collisions, it remains exactly the same. The only thing that changes is the effectiveness of collisions. The collisions or the proportion of effective collisions, it becomes a lot higher because the catalyst makes the collisions more successful. Okay? So ये सारा तो AS O levels, IGCSE already, you are kind of familiar with all of this. Okay? The wording has to be, I mean, you have to pay attention to wording. And then we did an example of heterogeneous catalyst, which is when the catalyst and the reactants are not in the same phase. This Haber processor, you've got gases, and the catalyst is a solid, right? It's a solid iron catalyst. So how does that work? I told you that it works because adsorption happens. Okay, you've got the iron catalyst. So what happens is when the N2 molecule approaches the iron catalyst, its electrons in the triple bond, because it was very hard to break the triple bond, that made the reaction very, very difficult. So that led to high activation energy. So what the iron catalyst would do is that it will pull the electrons towards itself, and it will weakly bond with those electrons. And in that way, the triple bond between the N atoms, that would break. Same is the case with the H2 molecule. When it approaches the iron catalyst, the electrons are going to be pulled towards the iron. And when the electrons in the bond are going to be pulled towards iron, they're going to weakly form bonds with the iron catalyst, which is why the HH bond breaks. So the first step is that the catalyst would weakly bond with reactant molecules. And the next step is deadsorption, which is that those weak bonds are going to break, and now the atoms are free to form new bonds. Okay, that is deadsorption, which is that the weak bonds between reactants and catalysts that would break, and new bonds can now be formed. Okay. Mama Binal Reid, is this clear?
Yes, sir.
Yes.
So next one, I'm just skipping the next part that we did, okay, because that involves a lot of electrochemistry. Let me just check. So now the next thing is we're going to move towards okay, before moving towards A levels reaction kinetics, we need to discuss वो कौन सा था? We need to discuss that thing, which is the Boltzmann distribution. So what? It's just a recap. You already know what the Boltzmann distribution is. That when you have, whether it's a solution or whether it's a gas, you've got particles that are floating around in a medium, and those particles, they follow a certain distribution. On one side, that's the proportion or the number of particles, or the percentage of particles. Okay, so this could also be referred to as the percentage, or it could be referred to as the proportion of particles. On the other side, it's on the other axis, you've got molecular energies. So how does the distribution look like? The distribution looks like that it's kind of a skewed distribution. This is how it looks like. Okay, that's what your Boltzmann distribution is. So this, so you've got low energy and you've got high energy. Okay, so on the axis, if the particles are on the left side, those particles have low energy, and if the particles are on the right side, then those particles have high energy. So you've got a low energy side and you've got a high energy side. Now there are certain points that you have to remember. This is the point. This is the energy. So this one over here is the most probable energy because it has the highest probability. I mean, particles that have this energy, you've got the greatest number of particles at this point. So this is the most probable energy. So most number of particles have this particular, they have this particular energy. And as you move forward, at high energy, you have fewer particles, right? So you've got fewer and fewer particles. The higher you go, the fewer the particles you have. And similarly, the lower you go, you're going to have you're going to have fewer particles as well. So remember, this is not the average energy. This thing over here is not, it's not the average energy of all the particles. Okay, so if you have a gas container and you've got a number of particles in that gas container, all of them are not going to have the same energy. Some would have less energy, some are going to have very high energy. So energies are always going to be randomly distributed. Particles would be colliding, some would be gaining energy, some would be constantly losing energy. So energies are randomly distributed. Uh, so some would have very high energy, some would have very low energy. Uh, so it's going to be a skewed distribution like this every time. Okay. There are a few things that have to be marked over here, and one is this axis over here, which is that this line over here. This is referred to as the activation energy. So any particle all the particles that have energies that are greater than activation energy, they're going to have successful collisions. So these particles are involved in, they're all going to have effective collisions or successful collisions because they have energies that are higher than the activation energy. When you add a catalyst, what happens to the activation energy? It decreases. So when you add a catalyst, so this is the same EA, and this is the EA for a when you add a catalyst to it. When you lower the activation energy, now what happens is that more particles are now going to be able to, they're going to be, previously they were not effectively colliding, but now the number of effective collisions increases. So let me describe this in words that, so what does the catalyst do? It lowers the activation energy. So it lowers the activation energy, and now, so more particles have energy that is greater than the activation energy. Hence, more effective or successful collisions happen. Okay. Is this clear to everyone? Remember AS ka recap hai, theek hai? Is this part clear?
Yes.
ठीक है, Raid clear hai? Mava, is this clear?
Yes, sir. Yes.
Achha, again, so I mean, isme AS mein na, this was pretty much it. There was one more thing, and that was that you had to, isko copy kar lete hain. There was just one more thing, कि if you increase temperature, you decrease temperature, what happens to this curve? So what happens to this curve is, it will shift hoti hai, just moves back and forth. So I'll just do all the working on this. As this one. So let me have the, so this is the activation energy. Yeah, add करना पड़ेगा. What was this? This was the number of particles or the proportion of particles. This was your molecular energy axis. As anyway, so what happens to the curve when you lower temperature? The lower करोगे temperature, it goes up, and यहाँ से it goes down. So this is what happens to the curve at a lower temperature. And let me explain. In lower temperature, what happens is that at lower energies, the number of particles increase because lower temperature. So at lower energies, the number of particles increase. And the number of particles at higher energy, they decrease. So you have more particles now at lower temperature, and you have fewer particles at higher temperature. So curve udhar se it goes down from the other side, goes up from this side. Okay. So this is what happens, and what happens if you increase temperature. So in that case, it becomes something like this. In that case, what happens is that the curve decreases. Lower temperature, you have fewer particles, and at higher temperature, you have more particles, right? So this is the same curve, and this curve is now at higher temperature. Okay? So you just need to know this. So I'm just going to write this down. Okay, again, this is AS recap. So the curve shifts to the right. And what happens to it? It flattens. So that is what's going on at higher temperatures, and what's going to happen at lower temperatures. At lower temperatures, the curve, it shifts to the left and rises. You get these two things. You've got to remember this. So the other clear, that's all AS recap. Is this clear?
Yes.
Okay, Baba, right? Is this clear? Now, clear or clear? So आगे, Baba, is this clear? अच्छा ठीक है. चलो ठीक है. अच्छा, now what we're going to do is we're going to move towards A levels reaction kinetics. Okay, so this is now the starting of AS A levels. बल्कि यहाँ पे I'm going to put a, ये खत्म हुआ this. ठीक है. And now we're going to switch to A-levels reaction kinetics. So in A-levels reaction kinetics, what you have is the first thing, the very first thing is we're going to talk about reaction mechanisms and the order of reaction. ठीक है. Before this, how is rate of reaction measured? Yeah, how is the speed measured? That's what the question is. I said, so rate or speed is basically what it's any change. It's any change with respect to time. That is delta time. So if there's a 100-meter sprint, so there's this person standing over here and he's running and he's supposed to and he's supposed to run let's say 100 meters. And I want to measure how quickly he's doing that, right? So he's running, he has to run 100 meters, right? So I'm going to measure the change and I'm going to divide by time. That's it, right? So it's going to be distance over time in this case because the change is distance in this case. Okay, so it's going to be delta distance, which is your change with respect to the time it takes. And you'll measure your physics, but you've already done this formula, which is that's what speed is, right? But remember, the reactions are not running. They're not really covering any distance. So in that case, what has changed? Okay, how could you figure out what that change is? Now, when it comes to reactions, that change could be pretty much anything. Okay, just a runner case where the change that's happening is the distance, right? So reactions where the change that is happening, it could pretty much be anything. It could be a color change. How quickly that color change happens. So you can time it. If it happens very quickly, that means it's a fast reaction. If it takes a very, very long time, then it's a slow reaction. It could be a change in concentration. How quickly is the concentration changing? Or also there could be a change in the volume of gas. Okay, if there's 10 cm3 of gas being produced, how quickly is that happening? You're going to time it. Okay, so if it happens very quickly, it's going to take less time. If it happens very slowly, it's going to take more time. It could be a change in mass, right? It could be pretty much it could be anything. How long something takes for dissolving, right? So the change could be the time required for dissolving something. It could be an energy change as well. I mean, maybe the energy is produced over a very long period of time, or it is produced very, very quickly. So so it's basically any measurable quantity that is changing during a reaction. It could be a pH change as well. Maybe during the reaction, the pH changes. So ये बात clear है? Is this clear? How rate of reaction is measured? Is that clear?
Yes.
Yes.
ठीक है. अब इससे आगे ये कि the other thing is that so for example, if I give you a reaction which is Mg plus 2HCl and it is producing what MgCl2 plus H2 gas. So this is a reaction. Well, in this reaction, how could you measure the speed of the reaction? You could measure the speed of the reaction by measuring so your rate could be proportional to the volume of H2 gas produced with respect to delta time. So you can do that, right? Or what you can do is you can measure rate by how quickly Mg dissolves. So your rate could be, the change could be the mass of mg over time. So you could plot that every few seconds. You can plot the mass of mg with respect to time, or it could be a change in pH. So you can measure the rate could be the change in concentration of H plus one. So remember, square bracket says concentration, right? So it could be a change in that with respect to time. With respect to time. So lots of things could be done for one particular reaction, and the graphs are going to look like this. So it's being for every at regular intervals, measure the change with respect to time and plot a graph. So at every time interval, measure the change that's happening with respect to time. So the graph would probably look something like this. Okay, let's say you've got a graph. So now if you're talking about the volume of phase two, the volume of phase two would probably, I mean, the graph would probably go up and then it will probably, it will kind of flatten out. So that is how the volume of H2 would look like. I mean, after a certain point, it's going to, I mean, it's nothing would be produced. So that's your change that you're plotting with respect to time. Okay. If you're plotting mg, the mass of mg, it's probably dissolving. So its mass will start going down, and maybe the reaction stops, so it stops changing at that point, right? So it could be the mass of mg. It could be a decreasing change. It could be an increasing change, right? ये clear है? You're making a graph. Is this clear? Our middle, is this clear?
Yes, sir.
Yes.
अच्छा, next है कि so it could be an increasing change. It could be a decreasing change. अच्छा, but what is rate? Rate is the gradient of this particular curve, right? So the rate is basically equal to it's the gradient of your change versus time. That's what, so that's what rate is. In graphs, and it doesn't matter whether the gradient is positive or negative. So for example, this gradient is good. So for example, this one, at this particular time, you measure the gradient and that's your rate, right? Now it's a positive gradient. For the red line, because the change is decreasing, for the red line, it could be a decreasing gradient. But it doesn't really matter whether it's a decreasing gradient or not. The sign does not matter. So the steepness is what matters, right? So the sign of the gradient is not an issue. So the sign of gradient is simply ignored. And the second thing is that you could have a decreasing change or an increasing change. So it could be decreasing, or it could be increasing as well. Yeah, or increasing. There's this one second. अच्छा चलिए कहाँ चला गया चलिए ये क्लियर है सारों को इज दिस क्लियर
Yes.
ये भी ऐड कर ले steeper curve means faster reaction. Again, this is not too different from what you already did. Achha, but the next thing is this is a very inefficient and a very but you don't actually do this. ये जो हम कर रहे हैं making graphs. ठीक है, imagine there's a 100-meter race. ठीक है, and there are runners and sprinters running, or there's a marathon race and people are running. No one starts making a graph. It's too time consuming. It's not a, I mean, I think it's a good way because you can now sort of, I mean, you can get all data points in this way. Imagine Usain Bolt is running and so every second, if 1 second, this is the distance, then 2 seconds, this is distance, 3 seconds, this is distance, and then somebody makes a graph. And then he takes the graph and he uh, measures the gradient at every point. So the point is, things are done because we're trying to measure the speed of the reaction, right? Well, no one really needs graphs. I mean, graphs are good because graphs would give you an idea about how the speed is changing. I mean, it was very fast initially, then it kind of slowed down, then it became flat. That means the reaction stopped. So graphs are good, but they're too time consuming. Okay, so especially in those cases, especially when you don't really care what is happening at every 1 second of the reaction. All you need to know is whether one reaction is fast or the other reaction is fast. So especially in cases where you don't care about what's happening at every 1 second, right? So where you don't care what is the speed. This is a 100-meter race, and we don't care what's happening. Who's running faster at 1 second and who's running faster at the third second. But we don't really care about the detail, right? Especially in cases when you don't care what is the rate at every time interval. So at every random time. And you're only interested in overall speed. So only interested in overall speed. So in that case, how is speed measured? Speed is measured. In that case, instead of change versus time, rate is just 1 over time. So where did change go? The change is going to be kept constant. So the change that's happening is kept constant in all the reactions. I mean, for example, if there's a 100-meter race, right? So what do? They don't go about doing any special math. All they do is they just measure the time. So since every runner is running 100 meters, whoever reaches 100 meters in the shortest possible time, he's the fastest, right? So that means rate is inversely proportional to time. But this can only work if the change that you're talking about is kept constant. So when I'm comparing reactions, and I'm interested in what is the overall speed of the reaction, right? So I'm going to time it for something. Now this change has to be a fixed quantity. So in a reaction, the timed change could be, for example, time taken for 10 cm cube of hydrogen gas to be produced. Now, for all reactions, some reactions would take longer time, some reactions would take would be very quick. So you're just going to measure the time taken for 10 cm cube of let's say H2 gas to be produced. So in that case, whoever produces it quickly, whoever produces it in the least amount of time, overall that is the fastest reaction, right? So is this clear? Okay, this is the formula that you're going to use. If you're just interested in the overall change, you don't want to see what's happening at every 1 second, right? So, Ichis, is this thing clear? ये clear है सारा को?
Yes, sir.
Yes.
अच्छा the next thing is that that's what you're going to do. ठीक है? So for example, the same reaction Mg plus HCl, right? You've got 10-gram piece of magnesium, right? So all what you can do is you can just measure the time it takes for 10 grams of magnesium to dissolve completely. In the second reaction, if it's happening at a higher temperature, and if it takes a lot less time, then that's a faster reaction. Okay, so you're keeping the change fixed instead of measuring change at every single time interval. Okay, so that is one way of measuring the rate of reaction. So now, mathematically, and normally what happens is, and most of the chapter that we're going to deal with after on, we will be dealing with this thing. Rate is basically change with respect to time. So, but we'll not be dealing with any change. We will mostly be dealing with change in concentration. So we'll be dealing with change in concentration with respect to time. Okay, this is in most of the questions. I mean, this change could be anything, but in our case, in AS, most of the things that you'll be dealing with would be talking about change in concentration with respect to time. So change in concentration, right? Now, for reactors, the concentration would be decreasing because they're going to get used up. For products, the change in concentration would be increasing, right? So this thing over here would be positive for products. Products would be increasing, right? And it's going to be negative for the reactant concentration because the reactants would be decreasing with respect to time. All you have to do is you just ignore the sign. Joe, we just talked about. I mean, we're just looking at how quickly something is happening. We don't care whether it's decreasing or whether it's increasing. The other thing is that if I have a reaction and in that reaction, I've got reactants and products. Well, the rate could be a change in concentration of A with respect to time. Okay, delta, forgot to add delta just a second. So it could be delta A over delta time rate. The rate could be measured with respect to reactant B as well. So it could be It could be the change in concentration of B with respect to time, or the rate could be a change in concentration of C with respect to. So you don't have one concentration. You've got multiple things whose concentration would be changing, right? The reactants would be they'll be used up and their concentration would be decreasing, and you're going to measure how quickly that's decreasing. Or the product concentration could be increasing, and you want to figure out how quickly that is happening, right? Yeah, the clear is this clear. So you're not depending on one reactant or one product. You could measure the rate with respect to any of them. Is this clear?
Yes, sir.
Yes.
Except for one thing, okay? Since it is one reaction, right? The rate of reaction value should come out to be the same, whether you're using the concentration of A, or whether you're using the concentration of B, or whether you're using the concentration of C. Every time the value should come out to be the same, but it's not going to come out to be the same, because imagine 1 mole per dm cube per second, or let's say 1 mole per second of A is getting used up. In the same second, how many moles of C would be produced? 2 times, right? It's going to be 2 moles that are going to be produced. So if I measure the rate with respect to A, the rate with respect to C would be twice as much. Because obviously, if 1 A gets used up every second, then 2 molecules of C are going to be produced. And similarly with B as well, if 1 A gets used up every second, then 3 molecules of B are going to get used up. So B's rate would come out to be 3 times higher. Is this clear as well?
Yes.
What you have to do now is you have to normalize. All these values should give you the same answer. And the way they're going to give you the same answer is that you divide by the coefficient. B and you're going to divide it by 1 over 3. C is you divide by 2. A would be divided by 1, obviously. You don't have to do anything. If you do that, then every time, it doesn't really matter whether you use A for measuring rate or B for measuring rate or C for measuring rate. It's going to give you the same result. So if this 1 mole gets used up every second, or 2 moles get produced every second, so this rate would be twice as much as A, right? But since it's getting divided by 2, it's gonna become equal again. So what you're going to do is you divide by coefficient to normalize the rate values. Now, issue नहीं होगा. You want to measure rate, you can use any of them. And if you divide by the coefficient, you're always going to get the same value. ये बात clear है? Is this thing clear?
Yes.
ठीक है, Bhava, is this clear? Clear है?
Yes.
ठीक है, बस यहीं पे छोड़ते हैं. We'll continue tomorrow then, ठीक है? चले, okay, Allah Hafiz.
Allah Hafiz, sir.